All right, the goal in this activity is to go through the exact same sequence of steps that we did for the spring mass damper with proportional control, now using this proportional and integral control. So now this has two terms, the Kp term and the integral term, which goes like Ki, some gain Ki times 1 over S. And so we're going to still look for the steady state error due to a step in the reference. So this really just means going through the exact same steps now with K, this K changed to be Kp plus Ki times 1 over S. And we're going to evaluate that steady state error due to a step in the reference. So go ahead and pause the video, attempt this, go back to the previous activity if you get stuck, and then I'll go through my solution. Okay, so now we're interested in doing this analysis with this new controller transfer function. So the closed loop transfer function actually stays the same. Again, we derived this just with a generic k. So now we're going to stick this k into here and down here into here. Ideally, you would actually go ahead and simplify this first and then stick k in the spots that it exists. So that leaves the pi, essentially the proportional integral pi part in both these places. So that leads to our closed loop transfer function looking like this. And now we're going to plug y into the error, definition of the error, which is just r minus y. So when you do that combination, remember y is just a function of r, so we get a common r term, and then we match denominators, and we do that subtraction, and that leaves us with this as the closed loop transfer function from the reference to the tracking error e. And now we're interested in knowing what happens when we have r be a step function. And so we put in 1 over s for r, and that gives us then this overall, where we take this out and put 1 over s, and that's our overall expression for the tracking error in the Laplace domain. And now we're interested in understanding what its steady state value, what this ESS is. And so that's going to be, we're going to use the final value theorem to do that. We'll plug this expression in for E and multiply by that factor of S. Again, that's convenient when you evaluate for a step function because that cancels out this term, this extra term of S that we're adding in. So that cancels with that. And when we do this analysis, now we're taking S goes to 0. And in this case, this term goes to 0, 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 and this linear term also goes to 0. And so what you're left with is 0 over Ki, which is 0. And so what this is telling us is the fact that when you add this proportional control term to your controller, that helps you eliminate that constant error that we saw that's due just from the proportional bit. And so that is a way to eliminate that without having to use the high gain approach that we did before. And that high gain approach essentially makes it small, but it doesn't actually make it 0. In this case, we're actually making it 0 in steady state. As long as Kp and Ki end up being stable, that's going to yield you 0 tracking error for this kind of reference. And so as you start to think through why this is working, it's useful to go back to the videos that discuss how proportional control works and where the motivation comes from for using this integral term, because essentially the gain that you'll be using, what you're multiplying the error by when it comes into this controller, this factor essentially gets bigger and bigger depending on the error. That's what the proportional term does, and then the integral of the error, which is what this term responds to. And so you can imagine that if you have a small error, but that it's persistent over time, that accumulates, and so that integral gets bigger and bigger the longer that's there. And so that's the factor that's really squishing that steady state tracking error down to make it 0, and that's why we get this 0 here.